Hi everyone, I'm Amir Hossein. In this training video I will show you how to simulate a VIIRS satellite sensor image using the WRF model output and RTTOV model. So you know that we use the RTTOV-Pi software tool. You can get access to the RTTOV-Pi software by cloning it from this repository on GitHub. After cloning, navigate to the directory, to the RTTOV-Pi repository, and navigate to the WRF data directory. I open the name list within the WRF data directory, and as I mentioned, our purpose is to simulate a VIIRS image. So the coefficient should refer to the VIIRS satellite sensor. Let me show you a notification about these coefficients. If you list all the similar notification of NOAA 20, let me show you that we might have different coefficients for the similar satellite. So for NOAA 20 we may have here we have 3 different coefficients. So you need to select the convenient, the suitable coefficient which is required for your simulation. For our case, this is the coefficient that is suitable for our simulation. Okay, this is the path to the WRF model output. As I mentioned, we want to simulate the VIIRS sensor image using the WRF model output. We extract atmospheric variables and atmospheric data from this WRF model output. This is the simulation time and simulation date and time. Of course, this simulation date and time must be coherent with the simulation date and time in the WRF model output. And this is the input data directory. You can change this data directory. It's arbitrary. You can select whatever name you like. And for the output data directory, for the output of the RTTOV model, this is the name of the output directory. You can of course change this name, but let us just leave them. And the next block is WRF DOS profiles. In this case, we don't want to simulate radiative transfer of dust particles, then we don't enable this block. We leave it as disabled. And this is the important block, the satellite information. The first directive, sat name index. What does this number 20 mean? Let me go to the RTTOV, the WRF data directory again. There is a auxiliary file information here, satellite name. You open it, we open satellite names, and in this file you can see a list of all the available satellites that you can use to you can simulate their images. So our simulation is about VIIRS data, and VIIRS is carried by the NOAA 20 satellite, and NOAA 20 satellite, the number of NOAA 20 satellite in this list is 20. So here we put 20, means that this satellite is actually NOAA 20. If it was something else, let's say if it was Landsat, you should put number 4. If it was Meteosat 9, you should put number 23, and so on. The satellite channel index, you should the satellite bands, the bands you want to simulate, you should put them in a list like this, and you should know what bands or what wavelengths or channels are available in a VIIRS satellite data. But also you can check it out by printing out the information, the wavelength information in the coefficient file. How can you do it? Just run Python RTTOV-PY with a flag wavelength and the argument, which is the path to the coefficient file. If you run it, it prints all the channels that are available for simulation. So we have 22 channels with the wavelengths. You can see the wavelengths here, and here we selected channel 17, 18 and 19, 17, 18 and 19. 17's wavelength is 3.6 micrometer, about 3.7 micrometer. Channel 18, the wavelength for channel 18 is 4 micrometer, about 4 micrometer, and the wavelength for channel 19 is about 8.5 micrometer. And the next directive is satellite channel name. This was the number of the channels, but also the channel names are important. You should put the exact name for the bands 17, 18 and 19. So you should know what bands or what channel names are available in a real VIIRS satellite data. This was the information inside the coefficient, the RTTOV coefficient, but for this directive you need to know the content of a real VIIRS satellite data, observational VIIRS data. And M12 corresponds to band 17, M13 corresponds to band 18 in the coefficient files, and M14 in the VIIRS satellite data corresponds to band 19 in the coefficient file. So for this information you need to check the real satellite data, the real VIIRS satellite data. This is the user defined position. We set position for the latitude 38 and for the longitude 45, and you could, of course, you could disable it, but in case of disabling this directive, the satellite might be outside of the domain. So this is the pure simulation. This is a pure simulation, and for a pure simulation we set it to be sure that the satellite is on top of our domain. Historical TLE for this case is not necessary, but if you enable it, you need to set your password and your username and password to the website spacerack.org for getting more accurate information of satellite position. But it's not necessary in this case. You can still get quite reasonable accuracy for the satellite position. So we just leave it as disabled. And post-processing and verification are the next steps. Just let me run it with these settings. Python RTTOV, let me see okay, let me remove the previous run here. I remove the previous output and then again run RTTOV-PY. This should be edited. Actually the WRF file was something else. Run it again. it runs RTTOV. It runs RTTOV Pi software and makes profile data for each grid points in the WRF model output. So here we have WRF, this new directory here, and inside this directory you can find the profile data on each grid point. And also we have a new shell script. This shell script can run RTTOV model for each of these grid points. One point that I forgot to mention is that you need to mention the RTTOV version and also the installation directory of your RTTOV model. So before working with the RTTOV Pi software, you need to install RTTOV on your system and provide the path to RTTOV installation directory on this for this directive RTTOV installation path. Okay, now that we have created the shell script for running RTTOV model for each of these profile data, I run it like this: arc G-Fortran. G-Fortran is the compiler that I use to compile the RTTOV model. Run it, and it runs and uses the profile data we just created in the previous step to simulate a radiative transfer on each WRF grid point using the profile data. I just terminate it because I have previously prepared this step, and I just copy it here. I just copy it here, okay? And yeah, and let me show you the content of this. Yeah, let me show you the content. The contents are profile data. The contents are the RTTOV outputs on each grid point. So if I open one of them, I opened one of them, and inside it you can see that the instrument is VIIRS. So it means that the simulation is for the VIIRS data, for the VIIRS satellite sensor. And here on the bottom side you can see the radiative transfer variables, brightness, temperature, calculated satellite reflectance, and you can see three numbers. These three numbers, they correspond to the three bands that we specified in the name list. Here I open the name list again. In the name list I specified three bands, 17, 18 and 19, and the exact number of values are here. So calculate brightness 302 goes for band 17 in the coefficient file, or the band 17 itself means the channel M12 in a VIIRS satellite data, and so on. The other numbers for band 18 and band 19. Okay, now that the VIIRS outputs are ready, we can go for post-processing. What does post-processing mean? Post-processing means that to make these data, these are actually separate RTTOV output on each grid point, WRF grid points. We want to make them to a single netcdf file. To a netcdf file, so we can visualize the netcdf outputs and have a map of the, let's say, of brightness, temperature, radiance, or other radiative transfer variables. How we can post-process it? We open name list. Go to the post-processing block here, the post-processing block, and enable it. Enable true. Leave the RGB plot brightness, it's not necessary. I just leave it as false. And image plot all bands, also set it as true, so you will have some image in PNG. Besides the netcdf file, you will also have some PNG images if you set this directive as true. I save it and I run RTTOV-PI again. Okay, and let me list the contents. In the content, one directory has been added. VIIRS post-processing. Go to this directory, VIIRS post-processing, and here you can see some netcdf files, radians for each RTTOV variable. For each radiative transfer variable, we have a netcdf file. What does this netcdf file contain? Let me open one of them. Let's say radians and see. Inside radians, you can see that we have three variables. These three variables, M12, M13, and M14. They actually correspond to the channels that we specified in our name list. I go again in the name list. I open the name list again, and in the name list there you can see that M12, M13, and M14. So here we have the simulated M12, M13, and M14. These are actually the simulated VIIRS sensor image for the bands M13. This is the simulated VIIRS data for the band M12, and this is the simulated VIIRS data for the band or channel M14. Now we have simulated band, we have simulated channel, and we also have the observational VIIRS data, so we can compare them. That can be basically a verification of the WRF model output, because we simulated this image using WRF model output. So I close it, I go to the name list, and in the verification I enable it true. And for the group file, if the group file is enabled, this directive satellite file path is ignored. So the group file is enabled, and the satellite file directory, inside this directory we have put our VIIRS data. Let me go to this directory. I go to this navigate to this directory, and in this directory you can find some VIIRS satellite data. These are actually the main. We have two satellite VIIRS satellite data. These two data, these are actually geolocation informations, and these are the band information, but both of them are needed. So if you miss the geolocation information, your data, these two files, they cannot be read by RTTOV-PI. And yeah, satellite sensor ID. This is also important. There is a difference between satellite sensor ID in this directive and here satellite name index. This satellite name index, this is the satellite itself, but this is the sensor of the satellite. you know, each satellite, they may have more than one sensors. So satellite is a different concept than the sensor installed on the satellite. So how did I know the sensor ID should be 62? 62 should be related to VIIRS data. Let me open the auxiliary information data. There is another auxiliary information data, satellite. You have two auxiliary information, one for satellite names and the other for satellite sensor. I open satellite sensor here, and it should be related to VIIRS. So 62, where is 62? 62, I go to 62 to see if it is correct or not. 62, yeah, it's about VIIRS data in HDF SDR format. So this sensor is related to the VIIRS data. It's very important because if you set another sensor, it will not be able to read the sensor. VIIRS. Yeah. And let me, yeah, you can see that you can find many VIIRS sensors here, or in other words, many VIIRS data types. It should correspond to the data type of your VIIRS. Our VIIRS data was HDF. Let me show it again to you. You can see that the format is H5, so they are HDF. So you should select a VIIRS index, a sensor index that correspond to the data type of your VIIRS. This is NetCDF, cannot be used. NetCDF, this is something else, and HDF SDR format. This is the format that is suitable for our observational VIIRS. So 62 was the index of the VIIRS of the sensor, and this is Taylor diagram name. You can change it if you like. Radiation Taylor diagram for VIIRS. If the sensor was something else, you could change it to diagram underscore something else, let's say MSG or MODIS or Landsat, whatever. And this is keep remapped satellites to the WRF data. This is also useful information. You can enable it. So if you enable it, your VIIRS data will be mapped on your WRF domain. And this is the name. You can change it if suitable. VIIRS to the WRF. I will show you what happens if you run it. And first let me change the environment because some other Python modules were required here. I didn't, I forgot to show you the outputs of post-processing. These are the post-processing that I forgot to show you. The output of the post-processing: overcast radiance, transmittance. These are some products: radiance, brightness, temperature, and of course you could use the NetCDF file for further analysis. If you need further analysis, you can use the NetCDF file and analyze the RTTOV output and simulation of your VIIRS sensor, VIIRS image sensor. And okay, let's get back to the WRF data directory. I run it again for verification. Now I want to verify it. verification is true. What does it mean? The verification means that we want to compare the post-processing, the netcdf file, which is the output of RTTOV, with the satellite observational data, with the satellite data here, with the satellite data. Run it. Verification processing on the satellite NOAA 20 band M12. It is actually reading these data and compare it with the outputs in this directory, the RTTOV output in this directory. Okay, now if I list it, you can find verification directory here. Go to the verification directory, and here we can see that we have 3 netcdf data. If you open one of these netcdf data for M12, this is actually the map of your simulated VIIRS image has been mapped on your WRF model output, on your WRF model domain. So you can see that the simulation of the VIIRS, how does it look like if you map it on the WRF domain. This is for M12 band. And also the comparison of it, we have 2 comparison, one for the Taylor diagram. This is a Taylor diagram. The first number and the second number, they correspond to band M12 and M13. For M14 it was not accurate, and it was outside of the Taylor diagram. And this is just a sample, just an example, and there might be some inaccuracies, but I wanted to show you how you could do the workflow. And one other important point that came to my mind, before that, let me show you radiation diagram table. This is also the information of comparing RTTOV simulations for VIIRS image with the real VIIRS data, observational data, the CV, RMSE, and correlation. And you can see that for the M14 band, the CV was very high and it was outside of the Taylor diagram. But for the first 2 bands, it was so-so, and it was inside the Taylor diagram. The important point I wanted to let you know, let me open the name list again. The name list in the simulation time is 2002. The month is 5 days 16, and hour is 10. And you should prepare satellite data, VIIRS satellite data, which are closest to this time. So how was our satellite data? The satellite data can be seen that here is day 22, the year 22, month 5, day 16. They are exactly the same in the simulation date, and the hour is 1 hour is near 9 o'clock or 8:15 in the morning, and the other is 10:30. And both of them are somehow they can be considered as the hour 10 in the name list. In the name list, they can be considered as, both of them can be considered as observation data for simulation at hour 10 here. So you need to try to find the closest satellite information to your simulation date and time. This is very important. If your purpose is verification, your WRF model output, maybe a wise act is checking out the available satellite data before even simulating the satellite image. So this was running RTTOV-Pi software. This was about running RTTOV model using WRF model output data, and simulating VIIRS image. And as you know, VIIRS sensor on top of NOAA 20 is a sensor on top of a LEO satellite. So LEO satellite is actually spinning around the Earth in a direction of north to south, or south to north, in that direction. And in the next videos I also discuss about how you can simulate a geostationary satellite like Meteosat or other geostationary satellites.